All right, we have made it to chapter 9, which is a great thing. I don't always make it to chapter 9, but we did that take-home test, and that really did buy us some time. And so the final exam, when is your final? I don't have the schedule. Is it on Tuesday or Thursday?
It's on Thursday.
It's on Thursday? Okay. Well, y'all ready? Two more lectures. Come on. You can do it. So look, here's the deal with chapter 9. I think that chapter 9 is really got some great information in it that can really help you if you're doing more math later. I think the material here is a little easier to deal with than the chapter 8 material. Because chapter 8, we started with sequences and we built all the way up to the Maclaurin series and Taylor series, and you kind of couldn't do Taylor and Maclaurin without a good understanding of all the other sections. This one, we're going to do 4 sections here in 2 days. I'll probably get through almost the first 3 today. And then we'll finish up the 4th one, the beginning of class next time, and then we'll talk about the final. So my plan is to bring in some sort of review that's going to list the topics that you need to look at, and then start doing some problems. I won't have time to go through every topic, but I'll kind of hand out the review and have you pick, hey, can you give us some sort of idea of what we would see from that topic? And I can go through some of those. Okay, so that's the plan. Okay, we are going to talk about parametric curves to start, 9.1. So to understand parametric curves, we first need to, everyone have a copy of the notes? I made these up yesterday so that you didn't have to write things down, you could just pay attention. Our traditional function, y equals f of x, right? When we said in the past, y is some function of x, and the example that I'm going to use here is x squared. The way that we first learned about these is like old school style. We had like a t-table. You go x, and then here you would say the y coordinate, right? And so you start plugging things in like 0 would spit out 0, 1 would spit out 1, 2 would spit out 4, -2 would spit out 4, right? Things like that. And so the input variable x here was called the independent variable, and then the output y was called the dependent. And in order for this to qualify as a function, every input had to go to exactly one output. So functions, when you say you have a function of x, what you mean is that it never happens that you plug in an x and 2 answers come out. That would fail to be a function, right? So we've got our graph here of x squared. And what's cool about this graph, what's useful about the graph is that when you look at the graph, you can actually see your input. In other words, like if I plug in the number 4, it appears on my x-axis, right? And the output appears up here, 16, right? This would be the point 4, 16. And so visually, you can see the input and output together, right? That's about to change. So that's why I'm pointing it out. Now, when we look at it this way, input, output, we can really use a slightly different notation and say that our traditional functions of x take a real number. So this is the double struct capital R, which we use for all real numbers. This takes real numbers and spits out real numbers, right? Your input's a real number, your output's a real number. I already said, notice that the x coordinate of the point, right, is the input. And notice also that to qualify as a function, it passed the vertical line test. That's back college algebra, right? We learned vertical line test. So we passed the vertical line test. And there is a problem, though, with our traditional y equals f of x function. So to illustrate the problem, I asked the question, can you graph a circle using a single function? So if we go and look at a circle, what's the problem that we run into trying to use a traditional function y equals f of x? You're going to have 2 outputs for a single input. In order to graph it, that's what's going to have to happen, right? If you're going to try and visualize your input, right? So if I plug in this x value right here, whatever that is, it's going to have to go to two different places in order for it to draw the circle, right? So that means you have an x getting plugged in that actually has to go to two different numbers, right? And it will fail to be a function. Now the easy way to see that was just vertical line test, right? If you draw a vertical line, it would fail. Now we can get around this a little bit. Okay, the way we could get around this is by taking a look at the equation of a circle, and in this particular case, the radius is 1, right? You'll see that? So this is the general equation of a circle. We could solve this for y, and if we solve it for y, move the x squared over, take the square root, but when we take that square root, what happens? We have to do the plus or minus. So now we've created two, those are our two outputs, right? That's what creates the two outputs. You give me an x, it's going to spit out both a positive and negative y. So to get around that, you could define two functions. F of x is, let's say, the positive answer, and g of x is the negative answer. And now if I graph f of x by itself, it will draw me the top half of the circle, and then g of x by itself will draw me the bottom half, right? But the question was, can you graph a circle using a single function? And the answer is no, we cannot at this point do that. Do you all understand the problem? Okay. Now, all the calculus that we've done up to this point has relied on our functions being functions, right? We needed y to be a function of x. Sometimes we could have that x was a function of y. We saw that when we were doing like areas between curves, depending on, sometimes we looked at the region sideways or vertically, right, our rectangles. So we could have that. We could have that x is a function of y. We could also have that y is some function of x. But we've never had to deal with the situation where we had something like a circle in trying to define it as a function. But circles are important to us, right? I mean, they obviously show up all over the place. So maybe there's a workaround. And parametric curves, that's the workaround, all right? So the way we're going to do it is this. Instead of having this concept that we're going to take a real number in and have our function spit a real number out, instead, we're going to have our function take a real number in and spit out something in R2. Now what this means is that we'll have a number go in, and what comes out is going to be a point, an ordered pair, an x and a y value. So the x value will somehow depend on what that number is, and the y value will depend on what that number is. What we don't have anymore is that the y depends on the x. You'll see the difference? So this number that we have that we plug in, we don't want to call it x, we don't want to call it y, so we call it t. We could have called it anything, but generally speaking for parametric curves, we call this input variable t. And then what it spits out is this point, right? And the point, the first coordinate, is going to be some function of t. And then the y coordinate will be some other function of t. So you give me the inputs. It's almost like these are two separate functions. They look back at the input and say, hey, what do you want me to, what do you want to do? Plug in 4, okay, I'm going to do something to it. This one's going to do something completely different, and that's going to give you a point on the graph. Understand? Sure. You'll have to see with an illustration, but you get the general idea here? Okay, so we have, take a real number in. That's the input, send it to an ordered pair. Keep note that the input is not necessarily the x-coordinate, so this t does not necessarily have to become t here, like x was x up before, right? This is something else. It could be anything. T squared, could be sine of t, could be whatever we want. T is like a clock running in the background. Okay, so what we're going to do is visualize or try to imagine that we're going to start drawing something, right? We're going to start a clock, maybe t starts at 0, and then plug in different values of t and draw dots. And as t grows, we keep drawing the dots and then put them all together and we'll have some curve. So you're not going to be able to see t in the graph. It's kind of in the background the whole time. Make sense? Okay, our first and most classic example is this example. We're going to try and figure out a workaround for drawing the circle. I'm going to try and draw a circle without violating the idea of it being a function, all right? So here's how I'm going to define it. I need to come up with something for the x-coordinate and something for the y-coordinate, right? And we're looking at the unit circle right now. Now, it's already in your notes. You can see what I use, but let's figure out how I came up with this. Can you all see what I used? What did I let f of t be? Cosine t and sine of t for my y-coordinate. Now, let me explain where that came from. What I did was I said, look, this point, we have a point on the unit circle. It has an x and a y coordinate, right? And if I create a right triangle, I know that this side right here is x, this side is y, agreed? This side is 1. And I want to be able to determine the x and the y with a single input. So as I move around the circle, there's something here that changes as I move around the circle, and that would be the angle of this in this right triangle. So I'm going to call this t. This is my parameter, right? If I tell you that the radius is fixed at 1, then if I give you t, do you agree I should be able to figure out what x and y are? Right? Just give you the angle, you should be able to tell me what x and y are. So to actually figure out that it's cosine and sine, just use your pre-cal. So what's the relationship between t and x? What's the relationship between t and x? Cosine, right? I know that cosine of t equals adjacent over hypotenuse, right? And x over 1, of course, is just x. So right there it is. It's just glaring at me. Like I should let x be cosine t. And then what about the relationship between t and y? Sine. So sine of t should be y over 1. So look, I'm going to just let y be sine of t. So if I make that conversion, right, then defining x to be cosine t and y to be sine of t, this should draw a circle. Now, I'm going to verify it now, but do y'all kind of get where it came from? Okay. So to verify this, x is cosine t and y is sine t. I'm going to make a t table, but this t table is going to look very different than t tables we've done in the past. I'm going to put t here, that's our input, but our output is actually a point, cosine t, sine t. All right, so let's start with 0. What would you get if you plug in 0 for t? So the clock is about to start. It's at 0, and where am I? So cosine of 0 is 1, and sine of 0 is 0, right? So I'm actually at the point 1, 0. Let me back up my clock here. Whoa, there we go. Okay, so I'm right there. See my little red dot? Now let's jump to another t. Now, I could plug in anything I want for t, but let's plug in something that we're familiar with so that we can evaluate it easily. So how about pi over 4? If we do pi over 4, cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is the same thing, right? So where will we be now? Right there, right? Now, I kind of skipped over some stuff, like pi over 6, I could have done that. If I did pi over 6, it would have gone in there, right? Because it would have been smaller between these two. Then I would have been at root 3 over 2, 1/2. But can you see as I let the t grow from 0, it starts to draw this circle? You'll see it? Yeah? Okay. Now, let me go back up to pi over 4. When we had the problem earlier of circles not being a function, the problem we had was that the vertical line test failed, right? So like we draw a vertical line, and we had to be able to draw both of these points at the same time, which we couldn't do, right? We'd have one input, two outputs. Am I going to be able to draw this point down here? Can I draw it? What am I going to let t be in order to draw that? I can go, just keep going around, right? And it's going to be right around, I missed it, oh well, 7 pi over 4. So if I go 7 pi over 4, it's going to spit out the point root 2 over 2, negative root 2 over 2. And so do you see that I've actually created the 2 points that used to be a problem with the vertical line test? But I've created them in a way that the inputs, right? Look at the inputs. There were 2 different inputs, right? And I got both points. So single input goes to single output. I'm not having that problem anymore, right? Is that clear? Now, what happens when I actually get back all the way around and I go to 2 pi? Now I'm going to draw a dot on top of another dot that I've already drawn, haven't I? Mm-hmm. Is that going to mean it's going to break down and not be a function now? No, it's still going to work, because when I get to 2 pi, let me put 2 pi here. Here's my table. When I get to 2 pi, what do I get? What comes out? 1, 0 again? And so you say, wait a minute, this one goes to 1, 0, that one goes to 1, 0. It's not a function. No, that's not a problem, because it's 2 different inputs, right? Mm-hmm. As long as an input goes to exactly one output, it doesn't matter if they overlap. So if I just let t keep going, it's just going to keep drawing a circle on top of a circle on top of a circle. And crazy as it may sound, this is a function. But we have to view it, our definition of functions is a little different now. So when somebody draws a circle now, right? Let's say you go on a game show where they like to ask math questions. And they say, hey, is a circle a function? You will say, it depends, right? Is that a function of x? No, it's not a function of x. Now, if you parametrize it, which means you come up with parametric equations for it, then can it be viewed as a function of x, or a function of t? Yes, it can still be a function, because for every single input, you have a single output. All right, so this is a good workaround. It's going to allow us to do things that we never thought we could do before. And it also addresses the functions that we've seen already, like y equals x squared. Maybe there's a way that we can still draw that, even though that is a function of x, right? We didn't even have a problem, but can we use this idea of parametric equations to still draw that? Well, again, I give it away because you have your notes. Here's t. Here's our ordered pair that's going to come out. Can you draw that curve? Can you come up with these 2 pieces that will still draw this? So t is going to go in. What's going to have to come out? You're going to need 0, 0, then 1, 1. And what I'm asking are, what are these 2 individual functions going to have to be? Okay, what do you want the y coordinate to always be? Squared. What squared? T squared. The x coordinate squared, right? So like if you plug in 1, you want this to be 1. If you plug in 2, you want it to be 4, right? If you plug in 3, it's 9. Negative 3, it's 9. So you just want that to be squared, right? But this squared, right? But what's this? Why don't we just call it t? Okay? And this one, t squared. So look, t comes in, right? And the x coordinate says, okay, I'm just going to be t. And the y coordinate says, well, I'll be u squared. Well, I'll be that thing squared, right? Wouldn't this draw the same exact thing as this one would? As we let t be 0, let's put examples in here. We get 0, 0. Plug in 1, we get 1, 1. Plug in 2, we get 2, 4. Plug in negative 2, we get negative 2, 4. You see, it's going to draw the same curve. And this works for any traditional function that you've dealt with in the past. So what if I change this? Let's go with something else. How about, let's say I wanted to somehow draw cosine x using this right here, this same idea, what would I do? T cosine t. That's it. And if this was square root of x, t root t, right? So all that happens when you go from traditional functions to parametric equations is you just replace your x with t, and you replace the y with whatever function you had, but make sure you switch it from x to t. Okay? So not only can we handle a circle, we can even handle things we've done already, right? So this works for things we've done already. And it works for things that used to not work, like sideways parabolas. What's the equation of a sideways parabola like that? Anyone know what that is? X equals y squared, right? And we would have said back in the day that this is not a function of x because it fails the vertical line test. But we can throw that out now. If we can come up with some sort of parametric equations for this, then it can still be a function. So let's think about this one. This is going to be t here, right? T's going in. And then, what do you think? T squared is the x, right? Because look, what is x? It's this thing squared, right? So I'm going to let this one be t squared. And what am I going to let y be? Just t. So look at this. You give me a y value, right? Give me t. What does this one do? It says I'm just going to be t. And this one says, oh, well, I'm going to be that one squared. And that's exactly what this one is doing. Y is just y, and x is whatever y is squared. Right? X, this is your x, is this thing squared, but if y is t, then it's t squared. Do y'all see how this is working? All right. But it also allows you to do some really cool stuff, like something like this. Now for this one, I put the parametric equations up here. All right? And so this is just something where I'm giving you this and I'm showing you what it looks like. And the reason I want you to see it, and I'm actually going to press play here, we can follow that little dot around, right? So let me back it up. Okay, so I'm starting time at 0. So I'm plugging in different values of t into those parametric equations, and I'm plotting all the points. And as I plot them, it starts drawing this. I think everyone would agree with me that this traditionally is not a function of x. And it's not even a function of y. It fails, both the vertical and horizontal line test. So there's no way that you could try and fix this. This is a disaster. But it's still a function. In terms of parametric, it's well defined. It never has an input that goes to two different outputs. Now, why would that be more interesting to us to be able to study things like this? Why do you think it would? Yeah, there's a bit of randomness to this path, right? And when you look at things in the real world, right? Let's say we're studying, I don't know, I'm going to make up a real cheesy example. You'd never study this, but let's say that we have a bug, okay? And we put it on the ground, and we put it at, let's say, like an origin. We just say, okay, let it go, and it starts walking around, right? So this thing starts walking around doing something. Before today, if we were going to do any calculus in terms of trying to find its instantaneous speed or anything like that, we would need that bug to be a very special bug, because if that bug decided to turn around and come back this way, we would be like, wait, you're not a function anymore. We can't study you because you're going to fail the vertical line test now. I can't do any calculus if you do that. But if we have this new perspective where we can actually have functions that turn back on each other like this, then the big question is, can we do the calculus? And the answer is yes, and that's what we're going to do. So once we establish what these curves are, we're going to talk about derivatives, which would be slopes of tangent lines on this thing. Talk about areas. So if this thing enclosed itself, can we find the area of what's inside? And even arc length. Arc length. We studied arc length before. We can do arc lengths of this. So you could have something moving through space going from this point to this point and then say, all right, what was the total distance traveled? Yeah? That seems useful. What would be even more useful is if this was three-dimensional, right? Because if it was three-dimensional, if this bug was allowed to maybe fly through the room, then we starting to get into like real-world type stuff, right? We live in 3D. Okay, so in Cal 3, that's what we do. We have parametric equations in Cal 3 where we have not only an x and a y, but we also have a z. And so each of those coordinates are dictated by some time function, and we have some path, and then we can talk about velocity and talk about length, arc length, things like that. And then later on, you get into ideas that are even...
The picture they use for the string theory, like almost like the 10th dimension.
The 10th dimension thing from, yeah.
String theory.
Yeah.
Looks like a little bit. That's what it reminds me of.
Yeah. So I hope I've kind of sold you a little bit on the idea that parametric curves and parametric equations are useful. Here's another one. This one's really interesting. If you take a wheel, okay, let's say you're driving down the road and you pick up a rock, right? You ever get like a rock stuck in the tread of your tire or a nail or something, right? And it's traveling, it's stuck in your tire. So here's my nail. And it's going to travel, it's going to be going around as I move, right? Well, what does the path of that nail look like? If you're an observer, that nail in your tire or rock has a very chaotic path, right? It's not circular. It's this weird thing where it goes up, and then there's a very violent change in speed here. You have a pretty good acceleration here because you're going to go from here to a different direction, right? Changing a pretty violent change in direction there. That curve that's being traced out is called a cycloid. Okay, have anyone ever heard of cycloids before? Well, that's what it's called. Cycloids actually have a very cool property that's not in the... Well, no, the book actually does talk about it. If you take a cycloid, which looks almost like a parabola, okay, but it's very special. It's not a parabola. If you take a cycloid and you take, let's say, an object that rolls, like a ball, like a marble or something, and you were to put it here, and you were to roll it down this cycloid curve, right, and then have it come here to the end, there is no other path that you can find that would get that ball from the top to the bottom any faster. So like, let's say you had another ramp that you built that connected these two even with a straight line. So you roll your marble from this straight line down the ramp to this point. If you actually do this physical experiment, the ball that goes down the cycloid path will get there before the ball that goes down the diagonal, even though it's a shorter distance. Okay, and it just happens to be a result of the way that gravity works, and it's a very elegant result. And it doesn't matter how you build this other path. You could have it be very steep like this. You could have it go shallow, then steep, then shallow. No matter what, if we had like 10 different paths and we put marbles all across top and everyone made their own path and tried to come up with the best one, no one's going to beat the cycloid. The cycloid's going to be the winner every single time. All right? And it's got another property that's even, I think, more amazing than that. And this one's going to probably blow your mind. And that's, if you look at this cycloid, if I take a ball and I start it right here, okay, and I let it go, it's going to take a certain amount of time to get to here, right? Okay, so let's just call that time t. Let's go t tilde, just so it's special. All right? T tilde is the time that it takes the ball to get from here to here. All right? Then I start the experiment over, and I get another ball, and I put that ball right here. Okay? And I let it go. How long do you think it's going to take that ball to get down here? The same time. T tilde. And it does not matter where you put the ball. If you put the ball up here and let it go, whoosh, it's going to get here in the same amount of time.
Doesn't matter the weight of the ball too?
Doesn't matter the weight. That's, now it does matter. I mean, there are some things, rotational inertia does come into play. I mean, it depends on the size. Like if these are different sizes, that would have an impact. But weight would not. The mass wouldn't. So I think that's crazy when you think about that, right? But think about it a little harder. If I let this one go, right? If I just let it go, is it right as I let it go, it didn't have any speed, right? So it's got to pick up speed and then get to this point, right? When this blue ball gets to here, it's going faster than this black one was when I let it go, right? So by the time the blue one gets to here, it's moving a lot faster. So a lot of people think, look, this one's got to get from here to here, right? This one's got to get from here to here. So obviously this is more distance, so it's got to take more time. But the change is that when this ball moves from here to here, it picks up more speed than that black one had when I let it go. And so the cycloid has this very unique property that the time it takes to get from one point to the next is independent of where you started on the path. That's crazy. I think there are roller coasters, a lot of roller coasters. I could be wrong on this, but if I were designing roller coasters, I think a cycloid would be a perfect curve to use because you're going to get them from the top to the bottom the fastest, right? Yes?
So, so you're saying that the time that they take all of that would be the same?
Yes.
But the speed would be different?
The speed where?
Like, let's say you start from the top or like in the middle.
Well, obviously, look, think about this. This one from here to here, it goes a certain distance, right? But it takes the same amount of time that this one does. So this one has a greater distance. So the average speed of this ball is going to be smaller than the average speed of this ball, which means that when it was moving from here to here, it picked up a lot more speed than this one had when I let it go. Just look it up, Google it, cycloids, and there's a special terminology for this, and you can see people like do the experiments and stuff, and it's really cool. All right, so but the reason I'm bringing it up is because that's another example of a parametric curve that we can only draw it with the parametric equations. So useful stuff. Oh, the parametric equations for this particular cycloid are given up here. 2, then the quantity t minus sine t, and then the y function is 2, and then quantity 1 minus cosine t. Pretty cool. All right, so in general, if I'm going to recap 9.1, I'm basically saying that you're going to have to come up for parametric equations. You have to define the x-coordinate somehow. You've got to define the y-coordinate somehow, and then possibly put restrictions on your time. This isn't always necessary, but sometimes you need to restrict the time interval. And so when we restrict the time interval, we will not use a and b. We will use alpha and beta. And that's so that we don't confuse it. When we've used a and b in the past, that's always been our restriction on x, hasn't it? Right? Our restriction on x between a and b. Here, we don't want to make any confusion. Alpha and beta instead, and we know that that's our restriction on time. All right? So t goes to a point, and then really good news is that your graphing calculators can do these. So if you have your graphing calculator, please take it out. If you don't, then you can just sit there. Now, mostly everyone in here has a Texas Instrument. Anyone not? Okay, so here's what I want you to do if you have your calculator. I want you to go to the mode. And then in mode, you should have some options there for like func or something like that, para, and then you have polar, and I think there's even an option for sequential, something like that. Yeah. All right, I want you to switch. The default setting is function, and that's like y equals f of x. But there's a parametric mode, so go ahead and select parametric, and then go to graph something. I'm assuming you know how to graph something on your calculator. There's like a y equals button or something like that to graph. Okay, go there and you're going to see something you haven't seen before. You're going to see it says something like xt1 colon x, or no, yt1. Y'all seen something like that? Or x1t, I don't know. Some of these vary from model to model. y1t, something like that. And then below it, what do you see? xt2 or something like that, and then yt2? Yes? Okay. x2t, y2t. So here's how this works. Your calculator is going to allow you to give it both the x function and the y function. So these are kind of grouped. To graph something, you have to give it two pieces of information. So when it says 1 here, this is like the first curve. If you want to do another curve, here's the second curve. So they're grouped in pairs. Does that make sense? So go ahead on your calculator. Let's try and draw that standard parabola, y equals x squared. Now we did that earlier. So what did we use for our x function when we were going to graph that? It was just t. So you're going to have to put t here. And there is a key on your calculator. I think your variable button. Well, not on all models. Some models, there's actually a t. Other models, the button says like x comma t comma something. Or you can do alpha t. But you just need to get a t in there, okay? So everyone get a t in there. And then on the other one, the y1, put t squared. And then hit graph. And you will see half a parabola. So what the heck happened? Why are you only seeing half the parabola? Because the default setting for your calculators in parametric mode is to restrict t between 0 and 2 pi. That's the standard default setting on your calculator. It puts t between 0 and 2 pi, and it does that because most of the time when you want to use parametric, there's going to be trig equations or trig functions involved. So what we're going to do is we're going to adjust this right now. So to adjust this, what you do is you go to Window, hit your Window button, and you'll see something there that says Tmin, Tmax. Y'all see that? Don't worry if it says T-step, just ignore that. Y'all see Tmin, Tmax, Window, Tmin? Change Tmin to -10 and change Tmax to +10. You can always go back and change it back to 0 to 2 pi. And then graph again, and you should get the full parabola. Okay? Now, graph this one, x equals y squared. And let's leave this one here. So just go to your next one here, and this time it'll be flipped, won't it? T squared here and t here. And when you graph, you should have your parabola open up sideways. You'll have them both, right? That traditional one and then the sideways one. So it's kind of good, right? Like maybe you didn't realize your calculator does have the ability to graph things that aren't standard functions, right? Let's do cosine t, sine t. You can keep these here and move on to the third one, or if you want to get rid of these, you can put cosine t, sine t in here. See what it does. Should draw a circle. Isn't this fun? Cosine t, sine t. Do you get a circle? Yeah? If you're enjoying this, try this. Keep this one cosine t, sine t. And on the next one, I want you to do 2 cosine t, 2 sine t. Tell me what you get. A bigger circle. Do you have any guess as to what the radius of that bigger circle is? 2. Now where's that coming from? Do you remember how we did this earlier? And I said, here's a point, x, y. And I was trying to come up with, how did I come up with cosine and sine? And we said it was a unit circle where this is 1. We called this x, this y, and this right here t, and I said that was 1. Well, what if it's some arbitrary radius like capital R? Then when you set up your relationship between x and t, cosine of t is not just x now, it's x over capital R, right? And if I multiply both sides by capital R, I get capital R cosine t is x, and that's how you define your x. It's going to be the radius times cosine t, and then the y would be the radius times sine t. Yeah? Pretty cool. We'll do one more. Any questions, though? Let's do one more. And don't type this in, okay? Don't type it in yet. I want predictions. T cosine t, t sine t. T cosine t, t sine t. Spiral, very good. Think about this number out front controls the radius, doesn't it? If that's 1, it's a unit circle. If it's 2, it's circle radius 2, right? But if you let it be t, then it's changing, isn't it? And it's starting out where? If we start at 0, right? T is 0, you're going to have a 0 radius. And then, as you try and start to draw the circle, your radius increases. So you try and draw, and it starts to increase the radius, and you start to spiral outwards. See that? We have really limitless possibilities here in terms of what you can draw with these things. You could probably draw a face. Yeah. So it's okay. I mean, you can have, with parametric curves, you can have curves that turn around on each other and loop inside out. And there's a cool one in Cal 3. There's an example of a parametric curve in three-dimensional space. It's called the trefoil knot. And it's a curve that actually ties itself into a knot. Like if you were to pull it tight, it would be a knot. So it goes and passes through. But it's three-dimensional, so you have to imagine like shoelaces kind of and curve through themselves. All right, so you can go on your own time and have fun. Maybe this weekend you can just sit around and graph things. All right, do you feel like you got your money's worth on that calculator now? Moving along. By the way, I sent an email out today, just right before class, and it has all the recommended homework problems that I think you should do for Chapter 9. I don't have any videos on those. I'll do my best. It's the last week before the end of the semester, and I don't know where I'm going to find the time to make those videos. So if you have any questions on those questions that I put up, or the problems I assigned, I'll be happy to provide you with some sort of solution. I think most of them are odds, so you can at least check your answer in the back of the book. All right, if we have these curves, 9.2, section 9.2 is about what calculus can we do with these parametric curves. And the first most natural question is, can we find the slope of a tangent line? Right? Can we find the slope of a tangent line? Now, I know some of you have taken physics. So when you're in three-dimensional space, if you're moving around, okay, in three-dimensional space, then a tangent line is going to give you some idea of, like, well, here's an example. If I had like a ball on the end of a rope and I was swinging it around, right? Yeah. And all of a sudden I let go of the rope, where's the ball going to go? It's going to travel tangent to the path that it was on at the moment I let it go. And so any object moving around doesn't have to be in a circle. If you know its path, then if you were to release it from that path at that moment and just let it go on its own, then the tangent would give you the direction of that. Now, when you're in three-dimensional space, we actually look at that as a vector, not a line. But here we're going to just look at it as a line. Just know that later on it becomes a vector, and then what's the difference between a vector and a line? It has a direction and a magnitude. So, but hey, that's Cal 3. All right, here we want to know what the derivative is. What's the slope of the tangent line? So we remember that dy dx was the slope of the tangent line, right? This was the slope m of the tangent line. But what we have are things that involve t in them, right? Our stuff has t in there, not x's. I mean, it does have x and y, but there's t's also. So what we do is we use this very clever little idea that we know what dy dt would be, and that would be dt would be dy dx times dx dt. This is just noticing that because of chain rule in Leibniz notation, that this is the same as this. And you can see that it's just because these would cancel out, and then you'd have dy dt equals dy dt. So this is like an identity. It's almost like me writing that 2 equals 1 plus 1, right? Dy dt is equal to that. Agreed? But notice in me writing it this way, dy dx is in here, isn't it? And so all we have to do is solve for this. And to solve for this, I just divide this through. Just divide this out on this side. And that's where this formula comes from. Dy dx, the slope of the tangent line, is dy dt over dx dt. Now I didn't put this in the notes, but let's talk a little bit about what that means. What is y? Well, y is some function of t, isn't it? Because it's parametric. So isn't this really just g prime of t over f prime of t? Remember, our y coordinate was some function of t, g of t. And our x coordinate was some function of t, which we called f. So to find the slope of the tangent line, all you're going to do is take the ratio of the derivatives of the individual parametric equations. Just make sure you do the y over the x. And that's it. That's a very nice, clean formula. So let's talk about the slope of a tangent line on the unit circle. So I have 4 questions here for us. First one, draw your unit circle, cosine t, sine t, 0 to 2 pi. Curious, make sure we are clear on this. Would this still draw the unit circle? If I left this right endpoint out, would that still draw the unit circle? You'd start here. You would start there, right? Start drawing around, and then you're supposed to go all the way up to 2 pi without actually being 2 pi, right? That would take you, that is every point there. It will close this off. Because it's the same as 0. Now if you did this, then that would leave an open hole here, all right? So you'd have to include one of the endpoints to draw the whole thing. So I kind of overdid it, okay? And I went past and I included it. But I didn't need to include the 2 pi. All right, slope of the tangent line at this point. So here's our unit circle. We should all recognize the point root 2 over 2 as being at 45 degrees, right? Root 2 over 2, root 2 over 2. That's one of our common points. And I would like to know what the slope of the tangent line is there. Any guess? Positive or negative? Negative slope? What do you think? -1 maybe? Seem reasonable? Let's see if it is. dy dt, dy dx, I did that earlier too. dy dx should be the derivative of g with respect to t or the derivative of f with respect to t. What's the derivative of g with respect to t? Cosine t over negative sine t, which is the same as negative cosine t over sine t. Just bringing the negative out. And yes, this is negative cotangent t. That's kind of weird to have cotangent t, so I put the t in parentheses because it's weird to have t next to each other like that. Agreed? That's the slope of the tangent line. Sorry, yes, that is the slope of the tangent line. But I want to know it at this point. So how do I get the actual slope of this tangent line? Plug in what? Pi over 4. Okay, so you have to remember that when we were doing slopes of tangent lines before, to actually get the slope, you had to plug in the x-coordinate to find out what the slope was. Here, we're not going to plug in the x-coordinate. We got to plug in the time variable that corresponds to this point. So you have to remember that to get out to this point, t, right, here, t had to be pi over 4. How would you know that? Well, you just got to be familiar with your trig functions, right? You got to be familiar. You got to know that this corresponds to this. So now, to figure out what the at t is pi over 4, the dy dx is equal to, I'm going to use this one because we may not all know what cotangent of pi over 4 is. So it's easier just to put pi over 4 into both of those. So you get negative, what is cosine of pi over 4? Root 2 over 2 over root 2 over 2, and then that's just going to give you negative 1. So it is. It's exactly what we thought it might be. How about, the question doesn't ask this, okay? But what if I wanted to know the slope of the tangent line at the point root 3 over 2, 1/2 instead? What would change? It'd be pi over 6 instead, right? So you would put cosine of pi over 6 over sine of pi over 6, and then figure out what that is, make it negative, and that would be your answer. All right? All right, let's answer the second question. Answer to the first question is negative 1. Second question says, what's the what? What? What's the equation of the tangent line, right? What's the equation? Well, we just need to go back and remember how we found equations of tangent lines before. Do you remember what we did? It was just a formula, wasn't it? y minus y1 equals m times x minus x1. Isn't that the formula we always use to find the equation of a line? We just need to know a point and the slope. And we know the point, right? It's root 2 over 2, 2 over 2. And we know the slope is negative 1. So it'd look like this. That's it. That's the equation of the line. You could solve for y, but that is the equation of the line. So, right? You could like distribute the negative through and bring that over and collect like terms and blah, but that's fine. Questions on that? Pretty straightforward. Where is the slope of the tangent line horizontal? What is that asking you? When is what 0? Derivative, right? The slope? When is that 0? Right? So let's go ahead and write it down again. It was negative, was a cosine t, right? Over sine t. That was our derivative, right? Okay, remember, a fraction can only be 0 when the numerator is 0, right? So I could multiply both sides by negative 1 to get rid of that, and then just set the top equal to 0. So when is cosine 0? At, I heard pi over 2 and 3 pi over 2. There are two places where this would happen. So this goes back to pre-cal, right? You have to knowledge of your trig functions. So this would happen at t equals pi over 2 and t equals 3 pi over 2. Right? That's where it would occur. And on our curve, remember our curve was this. Cosine t, y was sine t. That was our unit circle, parametric equations. If you plug pi over 2 into this, here and here, what would you get? So at pi over 2, you would be where? Cosine of pi over 2 would be 0, and then sine of pi over 2 would be 1. And then here, if you plug in 3 pi over 2 here, it's 0, and if you plug in 3 pi over here, you get negative 1. So these are the two places where we should have tangent line that's 0, right? Horizontal. Does that match up to our unit circle picture? That's up here and here, right? Tangent lines? 0? Yeah. Okay. Next question. Last question. Where's the tangent line vertical? So what is, I know when we said horizontal, we said, oh, okay, it's just asking when is the derivative 0. But when you say that we have a vertical tangent line, what are you really looking at? When does the derivative not exist? When is the derivative undefined, right? So you're going to say, when is dy dx undefined? And that would happen when the bottom is 0, right? So when is negative cosine t over sine t undefined? That's going to happen when sine of t is 0, right? Division by 0, it's undefined. And there are 2 solutions for that. This is going to, well, actually 3 solutions. 0, pi, and 2 pi because it was part of my interval, right? I have 3 t values that would make that happen. If I take these and plug them into the original parametric equations, we should get the point 1, 0, here the point negative 1, 0, and then this one again is 1, 0. So it really happens at 2 places. And those were our 2 ends. Okay. Cool. Areas. Okay, so if we go back and we remember, given a function, f of x is y, if we were to restrict this between a and b and talk about the area in here, we know we did all those little rectangles and stuff and added them up and that gave us the integral, but we know that this becomes the integral from a to b of f of x dx, right? The dx was the width, this was the height, and that's how we came up with that formula. What we're going to do now is try and convert this formula over to parametric. So first of all, this right here, f of x, is not the same as this f of t from our parametric. Remember, this is really just the y-coordinate, isn't it? It's the height of that point. That's the y-coordinate. And this right here is still the width, right? So that y is going to be replaced with what? If we go to parametric, the y is going to be replaced with g of t, right? So this integral is going to get transformed. This right here is going to become g of t. And then the question is, what's dx? So what we do is we take this right here and we differentiate it on both sides with respect to t. So the derivative of the left side here is dx dt. The derivative of the right side is f prime of t. And then we solve for dx by moving dt to the other side on top. That's what I did right here on this line. dx dt is f prime of t, so dx equals f prime of t dt. So this piece right here gets replaced with f prime of t dt. That goes here. There's one more change. What's the other change on this integral? We go from alpha to beta instead of from a to b, because we've changed our variable from x to t, right? So here, this was the restriction on x's. Now it's the restrictions on t's. Do you see why earlier I said alpha and beta? We don't want to mix it up with a and b. So alpha and beta. This is it. That's our formula. So if somebody gives us a parametric curve, we should be able to find the area below the curve down to the x-axis by running that formula on it. Shall we do it? Okay, good. We'll do it. We'll do one. And what would be, what